Welcome back, citizens. This time we're going to touch on very basic engineering for industrial refrigeration engineers. One of the biggest differences between the run-of-the-mill engineer and industrial engineers is that hopefully we actually fix things. We take them to bits and we put them back together. And there are certain things you should know about engineering materials. So we'll start by looking at some of the common engineering materials that you're likely to come across. Starting off with cast iron, steel, aluminium, brass, bronze, and copper. Now, cast iron is used for most compressor bodies. It is cheap, plentiful, and has some superb qualities. The bodies made from cast iron are very stable, are readily machined, and are extremely strong in compression. However, they tend to be very brittle and will not tolerate torsional stress or shock loads. Welding of cast iron is not easily achieved. It can be done, but it's not recommended. However, brazing can be quite successful. Due to the grainy makeup of it, it is generally tapped with coarse threads, as fine ones tend to strip or pull out. Now we move on to steel. There are many types of steel available. There's mild steel, which is used for general components. Carbon steel, which can be heat treated to increase its hardness stroke toughness. High carbon steel, which is generally used for low market cutting tools. High speed steel, quality cutting tools. Cast steel is generally for quality castings and precision parts. Forged steel, the likes of connecting rods, camshafts, etc. It can all be readily machined, welded or brazed. Aluminium, a chemical element 13 with a single Al. It's a soft, lightweight metal that can be cast, rolled and readily machined. It can be welded under certain conditions, and there are many different alloys made from it, usually containing zinc or magnesium. And some of these materials are known as pot metals and don't lead themselves for welding. Brass is an alloy of copper and zinc, and it has excellent corrosion and resistance and machinability. It's used in valves, expansion valve bodies, brass fittings, can be readily machined, welded or silver soldered. Bronze, similar looking to brass, is a copper and tin alloy, has excellent corrosion resistance and can be cast, rolled and readily machined. Copper is an element 29, symbol Cu, is a ductile metal with a very high thermal and electrical conductivity, and it's generally used for pipework, fabrications, electrical components, and can be readily machined, worked and welded. Now let's move on to screw threads and fittings. And the first thing I'm going to tell you is that bolts are sized by their diameter and not their head size. A lot of people make that mistake. So here we have on the left a bolt, and there we have on the right a set screw. Now you can obviously see the difference. The bolt is threaded part of the way along, and the set screw is threaded to the full length of the bolt. Again, remembering the size is the diameter of the shaft and not the head of the bolt. So let's move on to the grades of bolts. They are generally all made of high tensile steel. And how do you know what tensile steel they're made of? Well, if you look at the heads, these ones here, generally American type. These ones here, again, can be American. The reason that we use a lot of American bolts is because a lot of refrigeration started in America. Here we have the more common ones used in the UK, and the most general one is an 8.8 bolt, but it goes up to 12.9. Here you can see a torque wrench used for tightening bolts accurately, and there's a good reason why they should be tightened accurately. One thing I would say about these is when you've finished with it, wind it back to zero, because if you leave it with the spring compressed, pretty soon it will lose its calibration. Well, how do we know how tight to tighten a bolt? Well, you can look up a chart like this. It gives you the different grades of tensile steel, and it gives you the diameters. So all we do is, for example, look along an M10. It tells you the head size and then the different torque settings for the different grades of bolts. Now, there's one thing to remember, and that is that if the threads are oiled or lubricated before assembly, you tend to reduce the value by 10%. Now, the reason that we torque the bolts is because if we under torque them, obviously they stand a chance of coming undone. If we over torque them, we'll take them beyond their point of elasticity and the bolt will stretch and it'll be no good. Now we come on to washers, and we have the flat washer, the spring washer, and the shake-proof washer. The shake-proof and the spring are there primarily to stop the bolt coming undone once they've been tightened up. Here we have an example of some types of nut. We've got the hex, the heavy hex, a nylon, which we use quite a lot, a jam, which is generally used as a locking nut, and then you have the nylon insert jam lock, and down to the bottom right there, a prevailing torque lock, which is a non-reversible lock. It's similar to a nylock, but it's a lot more difficult to undo. Another way of stopping bolts from coming undone is wire locking. And if you see here, the bolts heads are drilled, and wire, typically stainless wire, or it can be soft iron locking wire, put in and twisted. And if you look the way that they're done, it would stop the bolt from undoing. Now we come on to tightening sequences of bolts. If you look at the square one at the top, it simulates a cylinder head off a car or a similar machine, and you would start in the center, 1 and 2, and then work your way out. So you're working from the center outward. That way you don't tend to warp the head or distort the head. When it comes to the flanges, like at the bottom, you need to work from one side, then the other, then the other, and the other. The reason why it's important to tighten these in sequence is so we don't end up with a misalignment like the one shown. I would recommend that you tighten them up and get them all square by hand first, or just nip them up and then carry on with the torquing. Thread types. Now, there are a plethora of thread types out there. There are fine threads, coarse threads, metric threads, imperial threads, pipe threads, and any other thread you can think of. Here we have a closer look at the threads. We have the major diameter, which is the outside diameter of the bolt. We have the pitch, which is the distance between two of the threads, in this case shown in the valleys. And we have the thread angle. Now the thread angle generally for metric or UNF or UNC is 60 degrees. If it was Whitworth, it would be 55 degrees. Okay, thread recognition. As I said before, there are many, many types of thread forms out there. The metric, for example, you've got coarse metric, standard metric, and fine metric pitch. In imperial, you've got UNF, UNC, BSF, Whitworth, BA, etc. Now, the tools that we use to determine the thread types are a measuring device, a screw gauge or a pitch gauge, and lookup tables. And that Zeus book is one of the handiest things you'll ever own. So I would recommend that you go out and buy one. Okay, so first of all, we want to measure the diameter of the bolt that we're looking for, or the thread that we're looking for. You can do that with metric vernier, imperial vernier, whatever you like. It's split up into different parts. You've got the main scale, which runs along here, and you've got the vernier, which goes along here. And if you were to read this, then you would look at it and you would count 20, 21, 22, and it's just over the 23. So your first measurement would be 23, and then you look along the vernier scale until they line up. You can see that that one lines up with a 6, so that's 0.06, and you add them together and you got 23.6. The other way to measure the diameter is to use a micrometer. Now, a micrometer is a little bit more sophisticated than a vernier. You can see like the anvil, the spindle, sleeve, the thimble, a ratchet stop, lock lever, frame, and a thermal insulator. And what's quite interesting is the thermal insulator's there to stop the frame from warming up too much by your hand, and thus making it less accurate because of expansion. Here we have at the bottom the drawing showing how you should read a micrometer. If we to look along here, you can see the main scale there, and it's split at the top between solid and half measurements. So you've got 5, 5.5, 6, 6.5, etc. And on the thimble, you've got little divisions, and there are some 15 at the moment. So looking at it again, we are up to 21, 22, 23. So it's 23, and the number that lines up is 0.15. So it's 23.15 millimeters. Okay, so this is how it's done. You measure the bolt diameter, again, not the head size, the diameter of the bolt, and then using a thread gauge, which is this bit here, you determine the pitch of the thread. So you basically take out each leaf of thread gauge and offer it up until it matches perfectly and you have no light showing between the gauge and the bolt. Having determined the pitch and the diameter of the bolt, we take out a trusty Zeus book and we look up in the reference table, for example, if it was a 10 millimeter bolt and a pitch of 1.5, then we would know it is an ISO metric coarse thread, 10 mil by 1.5. A quick look at how screw threads are made. On the left you can see taps. You have three types of tap. You have a first tap, second tap and plug tap, or taper, second and finishing tap. And on the right, for making male threads, you have dies, and there are two types of die. There's a solid die and a split die. Just to go back to look at taps again, you can see here you've got your first or taper tap, which has a lot of the threads ground away, that being so it's easier to start. The second tap has less ground away and will go down further into a blind hole, and the plug tap, which should again get you threads down to the bottom. So to start tapping a hole, first of all you look up the tap size drill for the thread you want to do. A good rule of thumb for metric is 10.5 by 1.5 pitch. thread, subtract the pitch from the diameter to get the tapping size. For example, 10mm diameter by 1.5mm pitch. You use an 8.5mm tapping size drill. So, you've drilled the correct size hole for the tap. You apply tapping compound to the tap. You start with the square in the hole, and it needs to be square. You don't want to be tapping a hole on the P. You turn it clockwise half a turn and then back an eighth of a turn to break off the swarf. You repeat until the depth is reached. And as I was saying before, if it's a blind hole, you follow up using the second and plug taps. Using a stud extractor, if you break a stud off or a bolt off within a casting or something, then the stud extractor is generally quite good for removing bolts and studs. However, there are a few pitfalls to avoid when using them. One, you need to drill the hole accurately in the centre of the stud and open it up as large as you can without damaging the threads. And it's quite important to get it as wide as you can. And using the tap wrench, not a shifter, so you get an equal and uniform torque, turn the extractor anti-clockwise. It has a left-hand thread, so it will bite into the stud and should remove it. Heat or penetrating oil could assist, but caution, if you snap the stud extractor off, you will need some sort of specialist drill to drill it out. And if you are removing from a brass fitting, make sure you drill it out first. Don't just use the extractor which fits the original hole. It won't be big enough and it will snap. Thread repair, a helicoil or thread insight, helicoil being a trade name. You can get a repair helicoil or thread insert. You get all the things that you need to repair it. You get the tool, the drill, the tap and the inserts. So effectively what you do is to drill the hole bigger, tap it out bigger, and then screw the thread insert in. And as you can see there on the cross section, it shows you exactly how it's done. Pipe threads. BSPP, British Standard Pipe Parallel. BSPT, British Standard Pipe Taper. NPT, National Pipe Taper. It's an American thread. FPT, Female Pipe Taper. MPT, Male Pipe Taper. BSP Taper. As you can see by the threads, they start off quite thick here and they taper down. And it's that tapering that does the sealing. Now, this is half-inch BSPT, and there's a picture of 14 TPI. The half-inch BSPT is half-inch bore of the pipe diameter and not OD as with copper. Here we have BSPP, otherwise known as parallel. As you can see here, the threads are paralleled and not tapered. And again, it's half-inch BSPP, 14 threads per inch, and it's the same. It's the bore of the pipe, not the OD as it is with copper. So, looking at taper thread sealing, the threads are sealed by the interference fit of the two components and the sealing medium. So if you look here, it's the interference fit there that does the sealing, whereas on the parallel one, it doesn't seal on the threads, it seals on the O-ring or bonded washer there. And there you can see a tapered male into a parallel female. Not a good idea. So, sealing BSP threads, taper threads, thread tape, PTFE, polytetrafluoroethylene. Ensure the tape is compatible with the medium to be sealed against. They have thread sealant, they have Loctite, etc. Ensure the sealant is compatible with the medium to be used. Observe the manufacturer's instructions for assembly. Sometimes they ask you to use a spray first, and sometimes they don't. Parallel threads, well, that's a different matter altogether. It's sealing washers, Delty seal, bonded seal, or a crush washer. Here you can see a Delty washer or a bonded seal. Delty washer being Delty being the manufacturer's name for a certain product. The seal achieved by the compression between the two flat surfaces, not the threads. BSPP and BSPT threads are not interchangeable. Pipe fittings. Here you can see some malleable iron pipe fittings. They're only pressure rated to 150 psi or 10 bar. So if you're sticking them on a refrigeration circuit and that goes off at 17 to 20 bar, these aren't going to cut the mustard. Brass fittings, we all use these. Depending on what make it is, they're rated between 48 and 83 bar G. A quick note on the sealing of a flare, copper flare. The flare joints are sealed by being compressed between the fitting and the nut, not on the threads. If there's a leak, there's no point wrapping PTFE around the threads. You need to cut the flare off and remake it. A quick look into the world of bearings. Going to look at different types and what they're generally used for. Ball bearings, probably most used in our industry. Now they're designed to absorb the loading going up and down or across that way. Roller bearings, very similar, but they will accept a much higher load than the ball bearings because of the large area of the roller. Taper bearings, they are very similar to the roller bearing, but they will also accept loadings going back and forward, and you have to set the preloading on the bearing. Spherical bearings, very similar to the rollers, but they will accept a certain amount of misalignment. You quite often find them on the cutting bar of an ice machine. Needle bearings, they tend to be used in the likes of connecting rod limb bearings, primarily using a high pressure cylinder on a two-stage machine. Seal bearings, as you can see here, the makeup, the outer ring, inner ring, balls, and also the seals, they have the right amount of grease to start with, and they hopefully sealed for the life of the bearing. If you're going to grease a bearing, you need to select the appropriate grease for it according to the manufacturer's specification. For general purpose, lithium soap-based grease or a food safe type. If you're ever looking to replace a grease nipple, you need to be careful, because going back to the threads again, there are loads and loads of different types of grease nipple sizes. If you come to use a grease nipple, there's certain things that you should know. One is always wipe it clean before greasing, because if there's any dirt or debris on that face, when you put the grease gun on, you're just going to end up pushing that into the bearing. And over greasing can cause as much damage as no grease at all. So don't be too generous with your grease. Benelling. So this is what happens to bearings when they're left and they're not moved on a compressor, etc. is standing idle for a long period of time. You got the load of the shaft pressing down on the top, and you get these little tiny points of contact. And if there's any vibration in the room, these are going to chatter up and down. The result is the points, the little tiny points of contact, you're going to end up with the pitting like this, and it's going to greatly reduce the lifespan of that bearing. So what you need to do is, if you've got something large, you need to turn it over every now and again and not let it set in the same position. Lip seals, very commonly used in our game. That is the sealing point on the shaft. And if you look here, you can see like that in the housing, and there's your sealing point there. So that's the oil side, and that's the air side. We'll take a quick look at overhauling a compressor. In this case, a reciprocating compressor. They're generally the only ones that you're going to overhaul on site. Screw compressors are just a mass of bearings, and they're better off being removed and sending back. Quite a common job on an open drive compressor would be the shaft seal. The shaft seal's there to keep the refrigerant in the system but still allow the shaft to turn. There you can see the shaft seal inside there. Now, just a word of caution if you're working on reciprocating compressors. If you see large studs like that, beware. It generally means that there's a big spring underneath the head. So you remove all the other bolts and gradually release the spring tension using the longer bolts. And as you can see by this cutaway, under the cylinder head, there's a big old spring pressing down on the discharge cage. Now, that's why you release the spring pressure gradually by using the long studs. Because I've seen in the past, people take off all the studs, give it a tap with the hammer, and that spring is very powerful. Quick look at shaft seal. This is a bellows type shaft seal. There are many different types. Here we have O-rings, one internal, one external. We have a carbon face, which is on the rotating part of the shaft seal. And we have the locking screws, which lock the rotating part onto the shaft. And the other part here is the steel, the stationary steel. Here's a cross section of a shaft seal. You can see there a gasket which prevents the gas from leaking out that way. You've got your two O-rings which stop the gas from leaking there and stop the gas from leaking there. And in between there you have the carbon seal which rubs against the steel part of the shaft seal, and that's what creates the seal and allowing movement. We move on to connecting rods, but the only thing you really need to be careful on these is match marks. When you're putting it back together, they need to be together, because otherwise when that was machined, it was machined that way. If they would have flipped that bottom round, it wouldn't necessarily be a round circle. Connecting rod big end shell bearings, they are made of a soft white metal, and they run against the crankshaft on a film of oil. Here you can see a crankshaft, and you can see where each bearing is sat on. So there's four rods on that one there. Generally speaking, you can get those reground if they're badly damaged, But there's not that many places now doing that, and it can also be very expensive. So what you do is you'd have it reground, undersize, and you'd have oversized bearings to make up for it. Generally speaking, 10 thou, probably 10 to 20 thou, you can have them overground. Connecting rod little end bearings, as we've seen before. This one's being bronze or phosphor bronze, etc. And these ones needle rollers. And as I said before, they're generally used in the high pressure cylinders of, for example, a Grasso. On the low pressure side cylinders, you would have this bearing, and on the high pressure, you would have this bearing. Parts of a piston. You see obviously the piston there, the gudgeon pin or knuckle pin, as some people call it. You've got your 3 sets of rings. The top ring is generally a compression ring. The second ring is a second compression ring, and the bottom ring would be your oil scraper. These clips here, circlips, would go in and secure the gudgeon pin in place. Now, when fitting piston rings, you set them up so that the gaps are 120 degrees to each other. The reason being it cuts down on gas leakage past them. There we have an assembled piston conrod assembly. There's your gudgeon pin, there's your big end bearing. You can see the white metal bearings in there. You can't really make it out, but the match marks will be there, and you have your tightening bolts. This little item is a piston ring compressor. It wraps around the piston and you tighten it up with that key, and it squishes the piston rings so it can be fitted into the cylinder. And there you can see the piston being fitted into the liner. So you would tighten that until it squashes in the piston rings, and then a gentle tap with a wooden end of a hammer, and it should slide nicely into the cylinder. Well, thank you for viewing, and if you have any further questions or require specific knowledge in another area, please contact me in the normal manner. Thanks very much. Bye.